Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back. Today we are going to learn about stress strain behavior of soil and rock. But before we take on the subject matter of today's lesson, we are going to look at the question set of the previous lesson. And this is the question set. The first question was, what are the differences between joints and fractures? So by joints, what I meant was there is no dynamic movement is responsible for the discontinuity, whereas in case of fractures there is a relative motion between the blocks on either side of the discontinuity. So joints, for instance, could arise because of the differential cooling of the original rock forming material, semi-solid rock forming material or magma, and because of that there might have been cracking within the body of the semi-solid object, and these things remain in the rock mass, and these features we are going to call by the keyword joint, whereas fractures develops later on during the lifetime of the rock mass because of relative movement between different portions within the rock mass. So that is the essential difference between joints and fractures. Then the second question that I asked was, a sandstone core sample of 55 millimeter diameter failed in a point load test at 17,000 meganewton force, estimate the UCS. So the problem here is like this. We have got a core sample, and that core sample has got a diameter of 55 millimeter, and this particular core sample was subjected to a point load test, and when P became equal to 17,000 meganewton, this particular core cracked. So this is the problem, and based on this data set we are going to try to find out the UCS, unconfined compressive strength of this intact rock specimen. Okay. So first of all, the solution what we are going to do is to find out the point load index I subscript s, and you recall from your notes from the last lesson, I subscript s in this case is going to be equal to 17,000 multiplied by 10 to the power 6 divided by 55, or the diameter of the core specimen, square, and the unit of it is going to be Newton per millimeter square, that is equal to approximately 5620 Newton per square millimeter or MPa. Actually, this unit is the same as MPa. So, then what we get from this one is UCS. Actually, UCS is going to be equal to I subscript S, and this expression was again given in the previous day's lesson, multiplied by 14 plus 0.175 times the diameter of the specimen, and that in turn is going to be equal to 5620 multiplied by 14 plus 0.175 times 55. Okay, let me get rid of a little bit of the material from the tablet. So, then what we get, let us begin from here. UCS then will be equal to approximately 133 Newton per square millimeter, or the same thing restated is 133 megapascal. Okay, so that is your answer. So, the estimated unconfined compressive strength of the intact specimen of this type of rock will be then 133 megapascal. Okay. So, that settles the second problem. The third problem was classify the following granite rock mass for a tunnel construction. The UCS for this an intact specimen of this type of rock was 150 MPa, RQD was 70%, joints were with rough surfaces and hard wall. The spacing of joints was 0.5 meter, and separation, joint separation was less than 1 millimeter. It had groundwater in it, the rock mass had groundwater in it under moderate pressure, and joint orientation was fair with respect to the tunnel alignment. Okay, so, our problem then is to find out the RMR. So, again you should recall your notes from the last lesson. UCS of 150 millimeter 150 MPa will give us rating of rating R1 of 12, then RQD of 70% will give us parameter rating R2 of 13, then joint spacing of 0.5 meter will give us R3 equal to 20. Joint condition will give us and R4 of 20. You should notice, if you have already dug out your last day's notes, then you should notice that this value of R4 is just a little bit lower than the best joint condition which was tabulated in the previous day's lesson. That number was 25, but the joint condition in this case was slightly poorer in comparison. As a result, we are using and R4 of 20. Then we have got groundwater under moderate pressure, that gives us an R5 of 4, and then we are doing the rating for tunneling with fair fair joint condition vis-a-vis tunnel alignment. So that gives us an R6 of -5. Then what we do? We add all these numbers and we calculate the RMR of 64, and again you look at the relevant table in your previous days lessons notes, and you will see that this value of rock mass rating will give us a classification of this. Okay, so the rock here is classified as a class 2 rock for the purpose of this tunneling work. Now, before I quit this example, let me take a few minutes to illustrate actually what I mean by a fair joint condition. Let us say you have got a tunnel alignment like this. So the tunnel actually goes like this. We are drawing, in this case, if you it is pretty easy to understand that we are drawing an isometric of the tunnel, and let us say the joint orientation in this case is like this. Joint sets are oriented with respect to the tunnel alignment in this manner. So this one here is one of the joints, and there is another one. So the other joint set is oriented in this manner. This is just an example. So here you have got this type of joint. Now you can see that this particular joint configuration is going to be bad for this tunnel construction, is because this much of wedge of rock just above the ceiling of the tunnel will always be prone to failure or collapse within the tunnel volume. So this particular alignment, so this is the unstable wedge in this case, unstable wedge. So this is going to be classified as unfavorable condition. On the other hand, if we had the tunnel passing through in an orthogonal direction, that means everything else was to be the same. Let us say the tunnel alignment, an alternative tunnel alignment was like this, where one joint set was oriented in this manner and the other one was oriented like this, exactly in the similar way as in the previous illustration. So these are the two joint sets that we are dealing with in this particular problem, but here the tunnel is moving rather than being parallel to the strike of the joints, it is moving perpendicular. In this case, the problem of rockfall is going to be much more limited. So, this one here is the tunnel alignment, and this one is the joint 1, and that plane there is joint 2. So, this is going to be called a favorable condition. Okay, so, that illustrates this particular aspect. And finally, before I wrap up the discussion and get into the subject matter of today's presentation, I want to take up a housekeeping point, and this is something to do with the classification of fine grained soil that I was talking about at the beginning of the last lesson. And there what I said is that you have got an A line. So, this one is the A line, and what we are doing is plotting the plasticity index against the liquid limit, and I said that in case of the IS code, you have got two vertical lines really at WL of 35% and WL of 50%. And you recall that this here, this zone here is MH, OH, whereas this one is CH, and so on and so forth. So, these areas there are several different classifications depending on which zone you are falling in. Now, in case of the ASTM code, this particular line is not there. This particular line is not there, and consequently you also do not have soil types that are classified as of intermediate plasticity or intermediate compressibility. So, in case of ASTM, you could only have CL or CH or CL ML, and then here you could have ML or OL. So, that is as per ASTM, whereas in case of IS code classification, your classification is a little bit more involved. Okay, so, that takes care of the point that I wanted to discuss, and now we get on with today's subject matter. So, what we want to learn in this lesson, we want to be able to define stress or strain at a point. Then we would be able to calculate stress and strain for coordinate transformation. We are going to define shear strength of soil and rock. We are going to define a simple failure criterion for soil and rock, and describe finally an experimental procedure for estimating the shear strength of soil or rock. Okay, so, those are the objectives, and then let us begin with the with what we mean by stress at a point. Now, you all know from your previous curriculum that stress is given by force per unit area. Now, that force could be a normal force. In that case, the stress is going to be a normal stress, or here what we are using the symbol, we are using symbol sigma to denote normal stress, or if the force is parallel to one of the planes, then the then the relevant stress is going to be called shear stress, and for this type of stress we are going to use symbol tau. So then we have got two types of stresses really, one is normal stress and the other one is shear stress. Now a graphical way of denoting or illustrating the stress at a point is by considering a small element, usually cubical element within the soil or rock mass, and that element is shown on the right side of this particular slide, and what we have here is a normal stress aligned in the vertical direction. So that is the only normal stress here on this particular element. Now we can have normal stress in other directions as well. So here we have got one of the pairs of normal stresses acting in the horizontal direction, and again and this is the second pair of normal stress in the horizontal direction. So in general, for a three-dimensional problem, you are going to have three normal stresses aligned in three orthogonal coordinate directions, and then you are going to have shear stresses. So we are beginning here with the shear stresses acting on the vertical plane on the right side of this particular element, and if you have got that kind of shear stress, in order to maintain equilibrium of this particular element, we are also going to have shear stress arising on horizontal planes at the top and bottom of the element, acting in clockwise direction in an opposite sense to the shear stresses that were operating on the vertical planes, on the corresponding vertical planes. So you should notice here that all the four shear stresses will act together in order to maintain equilibrium. All of them has to arise together, or they are not going to arise at all. So the magnitudes of each of these four shear stresses shown on this particular element is going to be the same. Okay. Similarly, we are going to have four more shear stresses. Here we are considering the vertical plane that is facing us, as well as the horizontal planes near the top and the bottom of the element. So all these four shear stresses are again going to be of equal magnitude, although the magnitudes of these shear stresses could be different from the previous four shear stresses that we considered. And finally, we are going to have four more shear stresses, and now our description of the state of stress of this particular point enclosed by the small infinitesimal cubical element is complete, and what we have here are three components of normal stresses, and what we also have is three more components of shear stresses and their complementary counterparts. Okay. So in general then, for a three-dimensional state of stress, we are going to have three normal stresses oriented in three orthogonal directions within the body, within the rock mass or soil volume, and we are also going to have three more shear stresses on planes, on three orthogonal planes. Okay. So then stress tensor within a point, within a mass of rock or volume of soil is going to be given by 6 independent components, and you should notice that the stress we are calling a tensor, and this is not a scalar nor is it a vector, because if you recall that in case of a scalar we do not have any orientation to worry about, whereas in case of vectors we had to worry about only one orientation, whereas in case of stress we have to worry about two orientations. One of those orientations are going to be the directions in which the forces are acting, and the other one is going to be giving the orientation of the planes on which these forces are acting. For example, we considered a normal stress, and that normal stress arose because of a force acting on an infinitesimal area A. So, we have to worry about the direction of the force as well as the direction of the outward normal to this infinitesimal area. So, we have to worry about two different directions in this case, and what we have in this process is not a scalar, not a vector, but we have got a quantity that is called a tensor, and any such quantity transforms in a particular mathematical way when we have to transform the system of coordinates from, let us say, x, y and z set of coordinates to x prime, y prime or z prime set of coordinate system. And we have got a mathematical rule that we can derive, which actually allows us to compute the 6 components in x prime, y prime, z prime system from the 6 components of the stress tensor given in x, y, z coordinate system. Okay. Now, here you should notice, getting back to the matrix here, you should notice that in case of normal stress we are having one subscript, and this is the subscript that defines the direction of the normal stress. In this case, the direction of the application of the force will be coincidental with the direction of the outward normal to this particular the infinitesimal area on which the normal force is acting, whereas in case of shear stress we have got two subscripts, and the first subscript in this case denotes the direction of the force that is acting on the infinitesimal area, and the second subscript in this case denotes the outward normal on the area on which the force is acting. So, let us illustrate with a small sketch here. Let us say you have got an infinitesimal element like this, and let us say in this case our x or say the y coordinate system is aligned in this manner, and the x coordinate system is aligned in this manner, and the z coordinate system is aligned in this manner, and we consider the top plane, the top horizontal plane of this particular element, and let us say we have got we have to name the shear stress that is acting in that manner, and you notice that as soon as the shear stress was occurring on the horizontal top horizontal plane, we introduced another shear stress occurring on the right vertical plane, and similarly you are going to have two more shear stresses on the two planes that are not visible from the front. So, we are going to have another shear stress acting leftward on the bottom plane, on the bottom horizontal plane, and one more shear stress that is going to act downward on the vertical plane, that is towards the left end of this particular element. So, we have to, our problem now is to name this particular shear stress. Now, you realize that this shear stress on the top horizontal plane arose because of an action of a force that was acting along the x direction. So, the first subscript which is going to go with this particular shear stress is going to be x, and since this shear stress is occurring on a plane for which the outward normal is aligned with the positive y direction, the second subscript is going to be given by y. So, these shear stresses are going to be called tau x y. Similarly, you could have tau x z and tau y z in when you consider the other planes. Now, you should also notice that all the 4 shear stresses in this case is going to be called tau x y, in spite of the fact that the shear stress acting on the bottom horizontal plane, which is acting leftward, that component is also going to be called tau x y, and that is because the outward normal on that particular plane is acting in negative y direction when the force because of which this particular shear stress arose is acting on the negative x direction as well. So, if both are negative, then we are not going to consider the sign, and if both are positive, then also we are not going to consider the sign of these things. So, tau x y will be the same as tau minus x minus y. Okay. Then let us consider the transformation in a 2-dimensional state of stress. What is a 2-dimensional state of stress? In which it is a state of stress in which we do not need to consider the third coordinate direction. So, here for instance, we have got a we are only confined within a plane element, not a cubical element as we were considering so far, and the directions we are going to consider in this case are x and y. So, what we are going to try to do in this case is say we are given a general state of stress on a 2-dimensional element in x y coordinate system. If we have got a transformed coordinate system x prime y prime, we want to be able to calculate what are the stresses occurring on that particular plane element. So, graphically stated, what we know in this case is sigma x, sigma y and tau x y. So, all these things here are known. We also know the coordinate transformation law, that means how we are going to transform x y coordinate system to x prime y prime coordinate system. That means we know this quantity alpha, this angle of rotation alpha, and our job here is to find out the quantities sigma x prime, sigma y prime and tau x prime y prime. That is our objective. Okay. So, what we do, actually we use a graphical construction in this case. You could do the same thing analytically, but what I am illustrating here is the graphical process, and the tool here is called the Morse circle. So, what we do here, we plot the states of stress on 2 orthogonal planes on a tau versus sigma plot. Tau is plotted on the vertical axis and sigma in this case is plotted on the horizontal axis. So, what we had there, if you recall, the element is sigma x and tau x y and sigma y and tau x y. Now, here you should notice that with sigma x we are plotting negative of tau x y, whereas with sigma y we are plotting positive tau x y, and that is because here we have to use another sign convention, that counterclockwise shear stress, a shear stress that wants to rotate an element in a counterclockwise direction is going to be considered positive, and shear stress that is going to rotate an element in the clockwise direction is going to be called negative. So, now we have got 2 points, and these 2 points represent the state of stress on 2 orthogonal planes. One is sigma y comma tau xy, another one is sigma x comma tau minus of tau xy. And if we draw a circle with a center on tau is equal to 0 axis, then the points on this particular circle are going to represent the states of stress on any other 2-dimensional element surrounding the point in question in case of a 2-dimensional problem. Okay. So, then what we do, our problem is to find out the states of stress on an axis rotated by an angle alpha in the clockwise direction. So, what we do then is to find out 2 diametrically opposite points which are separated by an angular distance of 2 alpha from the first 2 set of points, and the points on the second set of coordinates is called are going to be given by, in this case, sigma x prime, tau x prime y prime, and sigma y prime and negative of tau x prime y prime. So, that is the construction. It is a very convenient construction, and this circle here is called the Morse circle. Okay. Now, before I quit this discussion, I want to introduce 2 more objects, 2 more interesting aspects, and the first one is the major principal stress and the minor are the notions of major principal stress and minor principal stress. So, if you consider the 2 points on a Morse circle representing the state of stress at a point within a 2-dimensional element, then the point that is on the right end of this 2-dimensional element is going to be called the major principal stress, and you should notice that on this particular plane the shear stress is 0, and the one on the leftmost extremity of the Morse circle is represents a state of stress that is called the minor principal stress, and the shear stress on this point is also 0. Generally, the major principal stress is denoted using symbol sigma 1, and the minor principal stress is denoted using symbol sigma 3, and you may wonder what happened to sigma 2, and that is really when you have got a 3-dimensional problem, you have got one more principal stress, and that is called the intermediate principal stress, and for that we reserve the symbol sigma 2. Now, I should also mention here, which you have already noticed possibly, that in case of normal stress we are using the convention of compression positive and tension negative, and that is because rock and soil, they are very weak in tension. So, it is convenient to consider compression positive in this case. We also have got one more concept here, and that is the concept of maximum shear stress, and these are at the crown and at the bottom of the Morse circle, and in this case the one at the top is going to be called tau max, and the one at the bottom is going to be called negative of tau max, and tau max is really half of the difference between the major principal stress and the minor principal stress. Okay. Then we want to introduce the notion of strain within an element, and strain again could be a normal strain or shear strain. Normal strain is given by change in length of an element in a particular direction divided by the length of the element in that direction, whereas shear strain represents the change of angle within the element, and the expressions are given as stated on this particular slide. You should note these expressions. We are going to draw a sketch to illustrate these expressions. Let us say we have got a two-dimensional element like this. This is our x direction and that is our y direction, and let us consider a two-dimensional element, and the x dimension of the two-dimensional element is dx and the y dimension is dy. So, first of all, let us consider that by some means we stretch the element in the x direction, and this amount of stretching is given by du. It is a small infinitesimal quantity, and this definition is only going to work when the deformation is small. So, that will give us the normal strain in the x direction as du dx, as was given in the slide before. Okay. Now, let us consider another deformation pattern. In this case, what we do is we have got an element like this, and the element gets deformed in this manner. So, this is the deformed shape of the element. You should notice that the volume of the element does not change in this case. So, what is happening here is that this quantity is going to be called dV, because that is the change in dimension in the y direction, and using the earlier convention we are going to call this quantity here as du, and as before the undeformed dimensions of the element is dx and dy, or dx and dy. So, shear strain really is the sum total of these two angles, and since these angles are going to be small because the deformations are small, we have got this definition of engineering shear strain for this deformation pattern. Gamma xy is dV dx plus du dy, and this was the expression given in the previous slide. Okay. So, similarly you could define the other components of strain, and what you end up with is a tensor, again as was the case with stress, like that shown near the top of this particular slide. But you should notice here one change in comparison with the stress tensor is that you have to really divide the shear strains by a factor of 2 in order to compose the strain tensor. So, you cannot consider gamma xy, gamma zx and gamma yz like you did in case of shear stress tau xy, tau zx and tau yz, but you have to divide the strain quantities by 2 in order to compose the strain tensor. So, as was the case with stress, if you know the all the components, all the 6 components of strain in x, y, z set of coordinates, then you could calculate the components of strain in x prime, y prime and z prime set of coordinates. And it is obvious you could also think about a Morse circle of strain. Only difference is that if you recall, in case of stress we constructed the Morse circle by plotting tau versus gamma, but sorry, tau versus sigma, the shear stress versus shear strain, but here we are going to plot the shear strain quantities divided by 2 against the normal strain quantities. So, we are going to plot gamma over 2 versus epsilon in order to construct Morse circles for strain. Okay. Now, we can have, as was evident from the discussion that we had so far, a 2-dimensional problem or a 3-dimensional problem. In a 2-dimensional problem, we only need to consider 3 components of stress and strain. The examples of this include a plane stress problem or a plane strain problem. In case of a plane stress problem, you are really you have got a flat element. So, let us consider a flat plate for instance, and this flat plate is capable of supporting forces only in those directions. Then we are going to have a 2-dimensional problem. You could have actually shear stresses also occurring in this manner. So, this type of problem is called a plane stress problem. So, here let us call this one as sigma y, this one is tau x y, and that value there is sigma x. Whereas, plane strain problem, and this class of problem is more prevalent in case of soil and rock mechanics. Any problem which has got one of the dimensions very long in comparison with other dimension, like for example, you are trying to compute the stresses around a tunnel for instance. In this case, this dimension is very long in comparison with other dimensions, then this type of problem is called a plane strain problem. So, here what is happening really is in the long direction you do not develop any strain, or you can actually neglect the strain in the long direction. So, what you end up with are these components. So, you have got any strain component, if you call this long dimension as z direction. So, then in this problem you can neglect all those strains which has got a z in it. For instance, all these components, they are going to be non-existent. So, this class of problem is called plane strain problem, and this class of problem is called plane stress problem. Okay. And you could have a general 3-dimensional problem as well, where you need to consider all the 6 components of stresses and strain, of stress and strain. Okay. Then the question comes, how do we define, how do we derive the stress strain behavior of a soil or rock element, or a small piece of soil or rock. So, what we do typically is to conduct a triaxial test in order to find the stress strain behavior of soil or rock. So, here we take a cylindrical sample of soil or rock, and in this particular sketch the sample of soil or rock is here, and that sample is wrapped around within a watertight membrane, and then we place it in between two pedestals. So, this is the those are the pedestals, and then what we have, we enclose this element within a bath of water or hydraulic fluid, and this particular fluid is pressurized, and we then through a plunger near the top apply a deviator stress or apply a stress in addition to the pressure, to the cell pressure. So, the pressure here is called the cell pressure. So, this pressure is called the cell pressure, and this is the triaxial cell. So, what we do, actually we apply a pressure in addition to cell pressure through a plunger near the top, and we increase that stress, that is called deviator stress, until the sample fails or it cannot support any more any higher value of deviator stress. Sometimes these tests are carried out in a displacement control manner, in which a displacement, a constant rate of displacement is applied through the plunger on the top pedestal. Okay. So, that is how a triaxial test is carried out, and what you also should notice is that the top within the top portion, within the top pedestal, there is a porous plate, and the use of that will be illustrated later, and similarly there is another porous plate at the bottom, and that allows us to measure the pore water pressure within the element, and we are going to see, we are going to explain what is meant by that when we go further on soil and rock testing and one of the later presentations. So, this is how we actually conduct a triaxial test. So, what we do, the procedure is to apply a certain amount of cell pressure and take the sample to failure, and then you construct another, take another sample of the same rock mass or soil volume or the type of soil, and conduct another test at different value of cell pressure, and note down the new deviator stress, and conduct a series of such tests, and from that we can estimate the shear strength parameters of soil and rock mass. Okay. So, let us see how these tests are conducted. So, on the left is shown the schematic of a triaxial specimen, and that is subjected to an all round cell pressure and an axial deviator stress. So, let us begin the first test. So, what happens, we increase the deviator stress marked with an yellow color there, and we gradually increase that deviator stress. We take the sample to failure, and what we get are those responses. So, we have got a deviatoric response in which we plot the deviator stress versus the axial strain, and then we have got a volumetric response in which we plot the volumetric strain versus axial strain. And if you recall, volumetric strain is the summation of the axial strain on all three coordinate directions, on the three orthogonal coordinate directions, is going to give you the volumetric strain. And this is the response for the first test. And then what we do, we increase the deviator stress. We do the same thing as we did in case of the previous test, and what we get is this. Here you noticed that we increase the cell pressure. The cell pressure in this case is larger than the previous test, and we increase the cell pressure even further, and we do the same thing. We take the sample to failure by increasing the deviator stress. This one here is the second sample that we tested, and in case of the third sample we are going to increase the cell pressure even further, and what we get for the third sample is a situation like this. And then what we do, we will use these responses to plot the Morse circle for the three stress conditions in order to find out the shear strength parameters, and that process I am going to illustrate in the next little bit. But before I do that, what I want you to notice here is that as the cell pressure increases, you are going to be needing a larger value of deviator stress for in order to fail the sample. And also you notice that the amount of volume change in this case by increasing cell pressure, what we are having, we are triggering more of a contractive volumetric behavior of the soil and rock specimen. So these are typical responses of soil and rock samples. So here what we are doing is that on the positive side we are plotting volumetric expansion. So epsilon volume positive in this case indicate volumetric expansion or dilatation as it is called, and negative is contraction. So that actually gives you the response in a triaxial test, and based on this what we are going to do, we are going to plot the Morse circle concerning the stress condition in these triaxial tests, and we will be trying to identify the strength parameters from this series of testing of three cylindrical samples of soil or rock mass or intact rock. And what we are going to do is to estimate the sigma 1 value or the major principal stress value in each one of these tests and the minor principal stress value in each one of these tests, noticing that the horizontal and the vertical surfaces in this case are free from any shear stress. So they are really the principal planes or the planes on which principal stresses are acting, and plot the Morse circle. But we are going to continue this discussion in the next lesson, and we are going to see how we construct the Morse circle and estimate the strength parameters from this series of tests in the next lesson. So until we meet for the next time, bye for now.